All right, folks. So this is an example from section 4.7 on optimization. And so it's the example that we didn't do in class, and I want to do it on a video. So it says the following: let's figure out how long it takes for caffeine to be absorbed and released from the body. So the following function models the concentration C of caffeine in the bloodstream at time t. And we're given a function C of t equals 0.2 t times e to the minus t over 2. Okay. And the goal is to find when the caffeine in the bloodstream is the highest. Okay. So fortunately for us, we're actually just given the function, right? A lot of times in these questions in optimization, we know that we have to spend a lot of time building a function that, represents the variable that needs to be optimized, right? In terms of one other independent variable, right? So for example, drawing a picture to come up with an equation for the area of something or the perimeter of something, right? In this case, we were very fortunate. They just gave us the formula for the concentration. Now, of course, you might ask, well, where does this formula come from? Well, this is an interesting question. Sort of beyond the scope of our class, right? There are more advanced mathematical modeling type classes that you could take to learn how to build models that represent either, biological phenomena like this, or maybe physical phenomena or whatever, right? So that's sort of a more advanced thing in mathematics, learning how to build models like this. But we'll take it for granted, right? We'll say that we were given this model, and we have to, find when the caffeine in the bloodstream is the highest, right? So we're maximizing C. This is, the moment of time when, my hands are jittery and my heart is racing, right? Like that moment. Okay, so we're given the function C. We're not given an interval, right? And we know that one of the important parts of an optimization problem is to think about what interval is relevant, right? Because if I have a closed interval, a finite interval, then I can use the closed interval method, right? I can plug in endpoints and plug in critical numbers into my function and just look at what is the highest value. If I have an infinite interval, right, then I can't do that. And I need to use a number line test, right? So depending on the interval that makes sense, I change my strategies. So in this case, okay, let's think about what times t makes sense here. So certainly a lower bound, which makes sense, is 0. And I guess I technically could allow it to be 0. So I mean, I could make it a closed bracket at 0 if I wanted to. I doubt that 0 is the right answer, but fine. And what's the largest t value that makes sense here? Well, you might say, well, is it an hour, 2 hours, 3 hours? I really don't know. Just from this model alone, I don't have a good sense of a largest value of t. It seems like t can be anything positive. And so I should really allow my interval to go off to infinity. So, without any extra information, I think I'm going to have an unbounded interval in this case, an infinite interval. And so what I should really do then is use the number line test, right? So that tells me I'm going to use a number line test later on, okay? Like the first derivative test. So this is going to be a first derivative test for later, right? So I'm just making note of that for now so I don't forget later. Okay, so let's go ahead and optimize C. So I'll start by getting the critical numbers. So I need to take a derivative, C prime equals and I'm being very careful here because I notice that this is a product, right? T times e to the minus t over 2, which means I need to use the product rule in order to differentiate this function. So this is a product. Okay. So I'll take 0.2 out. And, just to be really careful, let me do this slowly. I'm doing first the derivative of t times e to the minus t over 2. Plus, leave the t alone, and then the derivative of e to the minus t over 2. And that equals 0.2 times, derivative of t is just 1, so that becomes e to the minus t over 2 first, plus t times, and now what's the derivative of e to the t over 2? Ooh, this is a chain rule, right? It's a little chain rule. E to the t by itself would just be itself, right? It'd be e to the t again. But here I have to continue the chain rule and take the derivative of minus t over 2 as well. Okay, so what am I going to get? I'm going to get e to the minus blah, so minus t over 2, times the derivative of the thing inside the exponential function. So the derivative of minus t over 2 is just minus 1/2. Okay, so I have a little chain rule in there. Be very careful. Okay, let me clean this up just a hair. So this is 0.2 times e to the minus t over 2. No, minus. Actually, I'll do minus t over 2 times e to the minus t over 2. Okay. So I have to be careful, right? Taking my derivative rules. But now that I have this, I can find my critical numbers, first checking where the derivative equals 0. So if I set this expression equal to 0, oddly enough, I see that the 0.2 doesn't matter. I can divide by 0.2 on both sides. And in fact, I can factor out, even better, I can factor out an e to the minus t over 2 on both sides, right? So let me factor that out. So I'm going to have e to the minus t over 2 times 1 minus t over 2 equals 0. Okay, so I did a couple steps of algebra there, right? First dividing by 0.2 on both sides and then factoring out a common factor. And now I have two situations, either e to the minus t over 2 equals 0 or 1 minus t over 2 equals 0. Now, in this first case, I know that there's no time the exponential function ever crosses the x-axis, right? So I know that this is impossible. There's no solutions here. The other half, I mean, this is a little easier to solve. 1 equals t over 2. And so I get t equals 2. Okay, so that's one of my critical numbers. I also should check quickly, right? Are there any times where the derivative does not exist? And given these functions, no, there's no issues here, right? No matter what t I plug in, there's no problems, there's no domain restrictions. So there's none of these. Okay. Just one critical number. This is typical, right, in these situations. I'll do my number line test with my one critical number t equals 2. And I should be careful. I don't want to plug in numbers less than 0, right? My starting point was 0. So, okay, let's think about plugging in some numbers into my derivative. And in fact, maybe it'll be easier. Here, I'm going to save myself a little bit of heartache. I'm going to try to plug it into the factored form of the derivative. So I'm going to copy that down here. You'll see why in a second. Okay, let's use some of our number sense type ideas, right? So, well, I mean, the easiest thing to plug in on the left half of this interval to the left of 2 is just plugging in 0 itself, right? I mean, so that should be okay. So c prime of 0, I'm going to get e to the 0 times 1 minus 0. And it's 1 times 1. I mean, that's fine. 1 times 1 is 1. And so on the left half, I have a increasing function. And then what happens after 2? Well, I'm going to try to plug in a super duper huge number like, 10,000. Okay, so if I plug in 10,000 into my derivative, what am I getting? E to the minus 10,000, 10,000 over 2 times 1 minus 10,000 over 2. And what do I notice? I notice that the exponential function is always positive times this is going to be a negative number, and I'm getting overall a negative number. So boom, negative number. So what have we learned? We have learned that the 0.2 is a maximum, right? It went from increasing to decreasing. So 2 is a maximum. Okay. And I think that's what we were hoping for, right? So we were looking for a global maximum. Yeah, caffeine is highest. And so just find when. So the when is 2, right? So we learned that t equals 2. Do we have units? I don't know if I have units on this. Hours? No, just t. Just 2. T equals 2 with no units leads to the maximum caffeine level. Wait, is caffeine EI? It is EI, yeah. Caffeine level. And that's it. So nice little practice, setting up our interval and then using our number line test to maximize this function. So if you have any questions, please let me know. And otherwise, I hope this example was interesting.